Have you ever wondered if time travel is actually possible? Get ready to satisfy your curiosity. E=mc² is perhaps the most famous equation in physics, derived by Albert Einstein to explain his theory of relativity. His theory is based off of classical relativity, which allows two people moving at different speeds to compare their speeds by stating their observations relative to each other. For example, a person walking at 2 miles per hour on a walking ramp with the speed of 3 miles per hour will seem to be moving at 2 miles per hour relative to the ramp. However, an observer standing beside the walking ramp will observe the person moving 5 miles per hour, the combined speed of the ramp and the walker. To reconcile these differences, the two people must add or subtract their velocity with respect to each other. So, the person on the ramp would add their speed, 2 miles per hour, to the speed of the ramp that the stationary person is observing. This results in the velocity that the stationary person observes, 5 miles per hour. This is classical relativity in a nutshell. Two people reconcile their differences in speed to achieve consensus on an observed velocity. Einstein accepted this version of relativity, but he also accepted equations derived by Maxwell, who became famous in the 19th century for the first colored photograph. Maxwell's equations combined knowledge of magnetism and electricity, and seemed to say that light traveled at a speed of 186,000 miles per second. Relative to what? Well, everything. Many people had trouble understanding this. How could someone who is sitting still and someone moving at immense speeds observe the same speed of light? This challenged the modern physics of the day. To reconcile these ideas, Einstein postulated that anyone moving at a constant velocity was still subject to the laws of physics. Since light is included in the laws of physics, anyone moving or sitting still would observe the same speed of light. How is this possible? To agree on the speed of light when motion is different, there may have to be disagreements on the components of speed, distance, and time. Two interesting concepts help explain these differences. The first is time dilation. When an object is moving incredibly fast, time relative to that object actually slows down. We can see this by looking at a clock. We all know that clocks measure time. How? By counting events that occur at regular intervals. A watch has gears that regularly turn. A grandfather clock has a pendulum that swings regularly. But at incredible speeds, like the speed of light, these intervals occur farther and farther apart due to the motion of the object. It's a crazy concept. Consider a clock that is powered by light bouncing back and forth between two mirrors. It bounces straight up and down between the surfaces at a constant rate. But what if the mirrors rapidly accelerated? The light photon would have to bounce in a diagonal path, forcing it to cover more distance before hitting a mirror. The regular event powering the clock has been slowed down, so time itself, by our definition, is slower. Another phenomenon that happens at incredibly fast speeds is length contraction. An object is shortened along its direction of motion. These are crazy concepts, but they've been proven time and time again by various experiments, and they help explain how a stationary person and a person in motion can observe the same speed of light. On Earth, it's hard to notice. That's because we can only move at speeds a fraction of the speed of light, so we've never noticed the phenomenon. So what does this have to do with time travel? Einstein based his theory off of a perception of reality known as the space-time continuum. This close relationship between space and time can be graphed on a coordinate plane of sorts. Now, everything is traveling through the continuum at a maximum available speed, the speed of light. But flashback to Algebra 1. The speed of light is the slope of the line on our graph. Some of the speed is being used to move forward in time along the y-axis, and some of the speed is moving forward in space along the x-axis. The more speed we devote to moving forward in space, the less speed is devoted to moving forward in time. If we could travel through space at the speed of light, we would be using all of our maximum available speed to travel in the x direction, and none would be left for the y direction, time. time relative to ourselves would stop. If we could somehow move at a speed greater than the speed of light, we could go backwards in time. Pretty mind-blowing, except don't worry, your elementary school teachers were not lying when they told you it was impossible to travel through time. We physically cannot travel at the speed of light. It's the universal speed limit, and we can't even come close to reaching that limit. Why? Photons, or light particles, have no mass. Having even a microscopic amount of mass makes it impossible to reach the limit. Take an electron, for example. With a mass of 9.1 times 10 to the negative 31st kilograms, electrons are essentially massless compared to humans. Yet even that little bit of mass would require an infinite amount of energy to accelerate it to the speed of light. Why? E equals mc squared. C, a constant, represents the speed of light, so the only variables, E and m, have a direct relationship. Increasing the energy increases the mass, which in turn means that more energy is required to accelerate a heavier particle. Applying an infinite amount of energy will only result in an infinite amount of mass, which demands more energy. The speed of light can never be reached. And how do particles gain mass, you might ask? That's a question for another day. Check out the linked video below to learn more. Hopefully this has helped satisfy your curiosity on the theory of relativity. I'll see you next time when curiosity calls.